for the globin gene. Because when you have 80% of the RNA as being one specific kind of RNA, you're very likely that most of the RNA is going to be globin. So that's one way of doing it, is to use RNA. Another way of doing it, sorry.
What was it?
Radio-labeled.
Oh, radio-labeled. Oh, right.
So it's radioactively labeled. So the way you do that is basically you can buy nucleotides, like ATP, that has a phosphate that is radioactively labeled. It emits beta rays. So you use a isotope of phosphate instead of that P32. So phosphate atomic number, I believe, is 31, and you have it radioactive, so it's 32. It's emitting beta rays as it's degrading down. So that's a radio. You incorporate that into your probe. So you basically use that radio-labeled nucleotide to make a copy of your probe, so that it now becomes radioactive.
So you saw that using isotope.
Yes.
Is this the case for every? Is like
You have to use some kind of an isotope, whether it's radioactively labeled or fluorescently labeled. You use an isotope that gives off a signal. It can be radioactive, but it can also be emitted. Yes. Well, otherwise you can't see the fragment.
Yeah.
So that is absolutely correct. Yeah. The other way in which you can make a probe is from a protein. You can get a sequence of a protein, and based on the sequence of a protein, you can make a probe because of the genetic code table. And so you can translate, go from a protein sequence to a messenger RNA sequence, so you can make a nucleotide. Alternatively, you use homology. Remember I said that if the globin gene is made from humans, it's going to be very similar to the globin gene from monkeys. And so you could make a probe of a globin gene from monkeys. When you have that sequence, you could make a probe that's going to be very similar, if not the same, to the sequence in human cells. And so you can use homology to do that. And these days, of course, you can use computer databases. Because we have all of these genomes sequenced, we already know what the sequences are. And so we can use those to just design the probes ourselves using the database. And then PCR and biofragment. So there are many different ways in which you can make a probe. Probes are obtained all different sorts of ways. So you don't have to worry about how the probe is made. Just assume somebody, a friend of yours, just gives you a probe or a piece of DNA and says, here's the probe, go use it to find additional information. Okay. So if there is a gene C in a large genome, now we're going from 2 fragments on a plasmid to the entire genome. Let's say we are interested in studying the globin gene. And we're interested in studying the globin gene for all of you individuals in the class. Well, how do we go about analyzing that? That's the question. So, we have a probe for the globin gene. Let's imagine gene C is the globin gene. We have a probe. Somebody cloned the globin gene from one of your individuals. That's your probe. So what you do is you isolate genomic DNA from each individual, separately, in a separate test tube. You digest the genomic DNA with a restriction enzyme. Any restriction enzyme that you're interested in, can be ECOR, 123, Banach, you name it. And then you run it on a gel. So it's exactly the same process as before, except instead of using plasmid DNAs, you're using genomic DNA. You take the DNA. Here's what genomic DNA would look like if it's not cut. It's very large, so it barely enters into the gel. So it forms a band right at the top. If you digest it with a restriction enzyme, it forms a smear. Because your entire genome is 3 billion base pairs long, and restriction fragments are of different sizes, and so they'll appear like a smear. Like a restriction fragment of this size, a little smaller, a little smaller, a little smaller. So you get this big smear. Hidden in this entire mixture of DNA is a sequence you are interested in. Let's say the globin gene. Somewhere in here is your gene of interest. And you want to basically know what is the size of this fragment in the genomic DNA for this gene, whether it's globin or whatever. So you take your fragment that's labeled, a probe. Here is the actual map imagine there are a whole series of genes, A, X, C, and R, and you are interested in gene C. Here are the restriction fragments for EcoR1. Okay. Different size fragments. Correct. There's a 1 kb fragment, a 2 kb fragment, a 3 kb fragment, a 4 kb fragment, a 5 kb fragment, etc. etc. So different size fragments. Your fragment of interest, in theory, is this 4 kb fragment. That's the one, right? But you don't know that initially because you're blind to it. All you see is this smear with all the fragments. Now you transfer this DNA to a membrane. So transfer it to the membrane. And then you hybridize it with a probe. So you have a probe that matches this gene. And now you get a band that matches and hybridizes like that. So out of this entire smear, one band will hybridize. And you will see it. And then based on this marker, you'll be able to say that this band is 4,000 base long. Now you have a map of that fragment of DNA from your genomic DNA. Right? And I can do this analysis for all individuals in this class very easily, no problems. Simultaneously, you basically run DNA from individual 1 in one lane, individual 2 in the next lane, individual 3 in the third lane, transfer it onto a membrane, probe it with that one single probe, and ask, do everybody have the same size fragment, or does the fragments vary in different individuals? So you can now analyze this one gene for everybody in the class very quickly, very efficient. So here is the map. Let's play a little with these maps. Okay? Now here is the map of this region. If I digest with EcoR1, we saw that there was a 4 kb map, a 4 kb map. If I digest with HinD3, which is a different restriction enzyme, I'll get different size fragments. So let's first do a digest with EcoR1. We're going to take this genomic DNA in a test tube. We're going to digest it with EcoR1. When we digest it with EcoR1, we're going to get a smear. We're then going to probe it with this probe, this little red line that's specific for this gene, gene C. And you find that it will pick up a fragment of EcoR1 that is 4,000 base pairs long. Right there. 1, 2, 3, 4. That band is at that 4 kb. So you can now draw a map, a restriction map for gene C based on this plot. And you can say that the restriction map looks like this for gene C. You can't say anything about the flank. That's blind. You're blind to those regions. Right? All you can say is that this probe lies within a fragment of EcoR1 that is 4,000 base pairs in size. That's your picture right now. It's like having a very dark room over here, and you have a flashlight. And with a flashlight, I can zoom in on only one individual, and I can get a picture of that one individual, basically, amongst the darkness. And that's what you're looking at. You're focusing in on this one segment of the entire genome, and you can start to build a little restriction map of that region. Using the probe. Okay, so now we have a small map of EcoR1. It's 4,000 base pairs in size. So we have a little picture of this. Let's now do a similar experiment, but instead of EcoR1, let's pretend this is blank. We are going to digest the genomic DNA with HinD3. Digest the DNA with HinD3. Run it out on a chip. It will look very similar to the digest of EcoR1. But now I'm going to probe it with the same probe. But remember, the HinD3 sites are not here and here. The HinD3 sites are here and here. So this time when I probe it, the band that will light up will be 8,000 base pairs in size. Correct? And so now, with HinD3, I can draw another map. And I can say, Cool. Here is my map. For that same region, digested with Hindi tree, I get 8,000 base step back. Right? Clear so far? So now I have two maps. I have a map for that same region with eCore 1. I have a map for that same region with Hindi tree. I can do a double digest. I can digest with eCore 1 and Hindi tree. Genomic DNA digested with both enzymes simultaneously. And then ask what is the size of the fragments. And I will probably find it's a 4 kb fragment. So that will tell me that the Hindi tree 8 kb flanks the 4 kb equal 1. And so now I have a much bigger and better picture of this region. And so you can build up a restriction map using this little probe right in gene C to get a picture of that region of the. So the point to remember is when you're using this method of southern blotting, there are two variables that are important. The restriction enzyme you use and the probe. Those are your two variables. Okay, so let's look at individual one. Here is what the pattern looks like. With eCore 1, you have 4 fragments that you generate. A 1 kb fragment, a 2 kb, a 4 kb, and a 3 kb. You have a probe, probe A. This probe will hybridize to this little blue spot. So on a southern blot, what size fragment will I see? And the answer is 2 kb. The probe doesn't have to be the entire fragment. It can be a segment of a fragment. It's basically a segment of a fragment, but it lights up the entire fragment. And so you're going to see a 2 kb fragment. So mapping chromosomal DNA with different probes. So if I take this DNA, digest with eCore 1, and probe with probe A, this fragment here that matches in this segment here, the size of the fragment I'm going to see on a southern blot will be 2,000 base pairs, or 2 kb. What if I have a probe that goes like this? What size fragment will I see on a southern blot? Will I see a 2 kb, a 4 kb, a 6 kb, or what? What's the answer?
4.
2 and 4. The reason is part of this probe will light up the 2 kb fragment, part of this probe will light up the 4 kb fragment. So you'll get 2 bands on a southern blot. You will see 2 and 4 because the DNA has been cut. So here's where I want to. So here are your. All right. So let's imagine this is what the DNA looks like. Okay? You've got a yellow fragment sitting next to a green fragment, sitting next to a blue fragment. That's your genomic DNA in your cell. The first thing you do when you start a southern blot is you digest with a restriction enzyme. When you digest with a restriction enzyme, you're going to break these fragments into 3 pieces. Right? Those 3 pieces are then going to be separated on the gel based on size. And so they're going to be on different places in the gel. Correct? They're not going to be in one spot in the gel, they're going to be in 3 different places in the gel. But now, I'm going to hybridize with a probe that spans the restriction enzyme, that goes on both sides of the restriction enzyme. So something that looks like this, yellow and green. And so this probe, because it has a region that's perfect with the yellow, will hybridize right there and label this path. The same probe also has a segment of green. And this probe will now also hybridize with the green. And so now you have 2 bands that will light up on a gel. So the probe, you always add excess of probe. You're not adding just 1 molecule of probe for 1 molecule of the genomic DNA. You're adding hundreds of thousands of copies of the probe for a very few number of copies of the genomic DNA. So there is excess of probe, so it will always find its match, irrespective of whether it's on one band or two bands or even three bands. And so it will light up. Now you have two bands that will light up. And so when you do this experiment here with probe B, you get two fragments lighting up, a 2 kb fragment and a 4 kb. Now with probe C, what will I get? You'll get only a 4 kb. For probe C. So depending on where the probe is, depending on what the enzyme is, you get different size fragments. Now, this is great. This is for one individual. Let's imagine I'm interested in a single gene, one gene. I could basically say, hey, I'll just clone this gene for that individual. So individual 1, I isolate the gene, I put it in a plasmid, and I get a cloned plasmid, I sequence it, I know the sequence of that region. But let's say I'm interested in analyzing the same DNA, the same gene from a totally different individual. In theory, I can do the same experiment. I can clone this piece of DNA in individual 2 and analyze the DNA there too, or individual 3 and analyze the DNA there too. So I could do this experiment by cloning. I could individually clone a piece of DNA from each individual that I'm interested in, and then I can analyze them by restriction mapping after cloning. But it's time consuming. Doing a southern blot is much, much faster. So I could basically just clone it once, clone the gene once from one individual, say individual 1. And then once I have that, I use that as a probe. And now I can analyze the DNA of individual 2 and individual 3 without having to clone the pieces of it. So I can run the DNA out on a gel from individual 1, individual 2, individual 3, individual 4, hybridize it to this gene probe, and ask what is the pattern to restriction map of that image. So, some more analysis of this. Let's take individual 1. Here is the probe, probe A. There's a second probe, probe B, that matches this 4 kb fragment. Individual 1 gives a specific band that's 2,000 base pairs long. Okay. Now, individual 2, using this probe, in individual 2, I get a band that's only 1,000 base pairs long. What does that tell us about this region of DNA in individual 2 versus individual 1? Okay. Basically tells us that either one person has an addition or another person has a deletion. There's either something that's added in, an insertion, or a segment has been deleted. So just by analyzing the size of the fragments, you can determine whether the gene has been deleted or an addition has been added into the fragment. We don't know which way it goes until we analyze DNA from many different individuals. If we know for a fact that this is the wild type individual, this is the mutant individual, then you can say, in the mutant individual, this gene has been deleted. There's a segment that is missing, and so the fragment is smaller. But when I analyze this fragment from individual 1 with probe B, I get a specific fragment of 4 kb. And individual 2 with probe B, I get a 4 kb. So probe 1 right here, or with probe A right here, individual 1 and 2 have a difference. With probe B, individuals 1 and 2 have no difference. So the probe and the enzyme determines what's going on. You will see a difference only with probe A. You will not see a difference with probe A. All right. So let's take a 5-minute break, and then we'll continue with additional types of models.
sometimes like microcellular.
I'm gonna try this out.
What?
Oh, you're typing in.
It has more to do with the
What?
charge.
You typed this first.
It has a negative charge in the paper.
So it goes out.
DNA.
What?
I don't know if the direct
You just got
the
it here.
direction matters.
You can listen to this.
They're all run on nitrous. They're all run on like an agarose gel. It's all like really similar to.
Yeah, left ear.
I said I wonder if someone asked me a question if they're doing. That's what attaches to your mind, so that you can visualize it.
I didn't know if it came up there. Look through it. Sure.
I got no choice.
She went to the bathroom? What do you say?
Wait, you showed me that one.
Oh, I know. That's why I stopped. I got headphones. But that sounds like mad right now. What did you want to say? No?
The one is sticking here.
Whatever.
I went then the bio lab. I told you that German.